previous lessons, we considered simple but at the same time well illustrative Deutsch and Deutsch-Jodes algorithms. We have also examined the ideas of quantum parallelism and quantum interference. We have seen that, compared with the classical counterparts, these algorithms are faster. Then we have looked at the quantum Fourier transform. And this quantum algorithm also turned out to be much faster and more efficient than its classical analog. In this case, however, the application of the quantum Fourier transform turned out to be quite specific, and in particular we found out that we could not use it as a classical Fourier transform for spectral analysis of data. However, then we were able to show that with its help we can still solve interesting practical problems, and on its basis we considered an algorithm for determining eigenvalues for some given unitary operator. It should be said that the use of the quantum Fourier transform and other quantum logical operations to create quantum algorithm on their basis in general, it is completely non-trivial task. On the one hand, this is due to the fact that the development of such algorithms requires serious preparation not only in mathematics and computer science, but also in quantum physics. On the other hand, this is due to the fact that this very idea of quantum computing appealed relatively recently, approximately in the 80s. It was considered only as some distant perspective. However, everything changed when it appeared that there are such actual computational problems that cannot be solved with the help of classical computers. At the first such problem was the problem of factorizing large integers, the solution of which was proposed by Peter Shor in the middle 1990s. In this lesson, we'll get acquainted with the Shor algorithm. We'll consider the following problem. Let a positive integer, composite number m, be given, and this number is the product of unknown primes p and q, and we want to determine these numbers p and q using the factorization algorithm. For example, it can be the number 15, which is the product of the prime numbers 3 and 5, or, for example, the number 93, that is product of 31 and 3. Such a task is of great importance for modern classical cryptography, or more precisely, public key cryptographic systems. The basis of such systems is the generation and multiplication of two large primes to encode information. Since primes are very large, it is impossible to factor the resultant number with ordinary computers in a reasonable time. For example, a modern classic computer needs to perform computations for about 10 million years to factorize a 1000-digit number. It turns out that such a problem can be reduced to the problem of finding the order or period r of the function ym of x, which is equal to the remainder of dividing the number a to the power x by the number m. Here a is an arbitrary integer which is greater than 1 but less than m and has no common divisors with m. For example, for m equals 15, a can be taken as 2. Argument x runs through all positive integer values from 0 to n minus 1, where n is a sufficiently large natural number that requires L classical bits for writing. L is determined by how many bits are required to record the number m. For example, 4 bits of information are required to write the number 15. The order or period of the function ym of x is called the smallest value of r different from 0, for which the value of the function ym, when divided by m, will give the remainder equal to 1. For example, let's consider the function y sub 15 of x, and this function equals 2 to the power of x, the remainder of dividing the 2 to the power of x by 15. And the order of this function r is equal
to 4. That is, we can write that 2 to the power of 4 is equals 1. If r equals to 4, then the value of the y function will be changing periodically, and I can write that 2 to the power of 4, the remainder of dividing 2 to the power of 4 by 15 is equal to 1. The remainder of dividing 2 to the power of 5 by the 15 is equal to 2. The remainder of dividing 2 to the power of 6 by 15 is equal to 4. And the remainder of the dividing 2 to the power of 7 by 15 equals to 8. And after that, all these values start to repeat. So let's assume that we already found an order of a function ym of x, and a to the power of r minus 1, remainder of dividing a to the power r minus 1 by the m is 0. Then we can write the following expression. The remainder of dividing the product of a to the power of r and half minus 1 and a to the power of r and half plus 1 by the m is equal to 0, or the product of a to the power of r and half minus 1 and a to the power of r and half plus 1 equals to lambda m, where lambda is the obtained expression is useless if r is an odd number. It is also useless if any of the factors of the left is multiple to m. But the probability of these two situations is lesser than 1/2. Otherwise, one of the factors on the left will have common divisor with m, and this divisor could be found with help of classical Euclidean algorithm.
If it is possible to determine the order of function, that the prime factors of the number n can be found using the classical Euclidean algorithm as the greatest common divisors of the number m and either the numbers a to the power of r in half minus 1 or the number a to the power of r in half plus 1.
Now, we'd like to consider the example for a classic Euclidean algorithm and find the greatest common divisor of the real numbers 408 and 112. To do this, we must first of all divide the first number by the second. So we can write here 3 minus 336, and the remainder of division is 72. Now, we should divide the number 112 by the 72, and this is just 1 minus 72. The remainder of the division is 14. After that, we divide the 72 by the 14, and it's also 1 minus 40, and the remainder of the division is 32. So let's continue our algorithm and divide the 14 by the 32. It's 1 minus 32, it's 8. And at the very end, dividing the 32 by 8, we obtain that the remainder of that division is 0. So, that we get the sequence of numbers and the last number, last non-zero number of this sequence is the greater common divisor. So, greater common divisor of two numbers 408 and 112 is 8.
Let's now consider the classical Euclidean algorithm. According to this algorithm, for two positive integers, a and b, among which a will be greater than b, the greatest common divisor is sought by composing the strictly decreasing sequence of numbers a, b, r2, r1, r2, and etc. rn, when the number r with index k is a remainder of dividing the number rk minus 2 by rk minus 1. The last number Rn of this sequence is the greatest common divisor of the numbers a and b. Здесь должен быть захват экрана. We have made all the necessary preparations, and now we are ready to consider the implementation of Shor's quantum algorithm. However, we will do it in the next lesson. That is all for now. Thanks for your attention.